Good morning, and thank you all for coming. Let's open the morning with the talk on exceptions, which is somehow undeservedly considered to be an exciting or a controversial subject. In truth, exceptions are one of the most boring parts of C++. And my goal is actually to convince you that this is one of the most boring parts of C++. And the reason is because, there is no real controversy about using if then else. I mean, what's so special about if then else? I mean, you just use it. There is no, code styling guys that avoid if then else. Nah, use goto. But there are plenty of organizations who outright forbid exceptions because mystery happens. Who works in an organization that does not allow use of exceptions by feet of law? There are some, like if you are in embedded systems, maybe, but for the most part, it's a result of kind of mystification of exceptions more than clear thinking. Furthermore, even if you don't use exceptions, as I said, exceptions themselves are very boring. Even if, just like if you don't use for loop, you still have some form of iteration, it just looks differently. And understanding how for loops work would help you write iteration in any other way, whatever that may be. There is very little in exceptions that is exception specific, so understanding how exceptions work would help you write better programs, even if you actually end up never using exceptions. Okay, with that, I think it's time for us to start on the subject. Let's go sit down. Okay, let's begin. So I already started talking about the motivation. I will show the basic exception machinery just so we're all on the same page and we know basically what the vocabulary is. And then we'll fundamentally switch to error handling. And at the end, I'll talk about the practical guidelines for using exceptions in existing code base. As I said, it's not actually very hard to use exceptions. It's harder to use them well, but even that is not particularly hard. I want to show that basically they are not special in any way. If your program is written correctly, and you want your programs to be written correctly, okay, just on that subject, just checking. Anybody works for organizations whose style guide says do not write correct code? Okay. What is an exception in C++? Exceptions are a language facility for handling basically abnormal situation. Usually there are some sort of errors. The non-trivial thing about exceptions, they interrupt a normal control flow. We'll see how that happens. And there is a reason for that. They are used when the normal control flow becomes impossible or at least undesirable. That's why they interrupt the normal control flow. And they create alternative control flow, which is executed only when exceptions happen. I'm not going to give you like all details about exceptions. You can read the standard, you can read the exceptional books, you can read CPP reference, but I'll give you enough basics for us to get through. So this is basically all the exception language, like almost all the exception language on one slide. There is a throw, there is try, and a catch. So we'll go through the explanation. So exception is generated using a throw. Here I throw an integer. You can throw anything you want. The standard provides the base class std exception. You don't actually have to use it. You can throw built-in types. You can throw your own types. You can derive from std exception. You don't have to. There are some advantages to that, but you can throw anything you want. Exception is arbitrary data type. It may contain data. You can throw a string, std string. You can throw a temporary, it just gets copied. So what happens when the exception is thrown? Well, let's go back here. It interrupts the normal control flow, so you immediately jump to the closing curly bracket. Any destructors that were for objects local in the current scope fire, the objects get deleted. And then if the exception is not caught by a catch block, this process continues. You jump to the next closing curly brace and so on. If doing so you reach all the way to the main, an exception is still not caught, the program terminates. There is an interesting detail here, which is that if the compiler knows, and usually it does, that you would reach main all the from the point where you throw, the compiler is actually not required to go through this routine. It can terminate your program right there, which means the destructors do not fire. I mean, the program terminates right there, but the cleanup does not happen. Well, the operating system presumably does the cleanup. So let's look at this example. We have some while loop. We create an object, and we're going to transmogrify it, except before that we're going to throw. Of course, you never write this, you don't throw unconditionally, but let's say we throw. What happens? Well, first of all, the rest of the code within that scope is not executed, so transmogrify is not called. Now, G is destroyed, local object, and the exception is not caught. Would that work, actually? Okay, I think it only works if I... Okay, so a local variable is destroyed. There is no catch here, so we keep unwinding the stack. Another local variable is destroyed here. Maybe. Why maybe?
It's going to escape all the way out.
Exactly. As I said, not caught anywhere on the slide. Now, in this case, you actually know that it's not caught, which means the compiler knows too. The compiler can call terminate right from here. Okay. Let's change it so we catch. So now this has to be destroyed. So now in this scope, when we throw, we know that there is a catch. Compiler actually tracks that whether there is at least one catch in the stack above you or not. So now there is a catch. Local variables are destroyed. Okay, I'm sorry, this would actually be called. This is incorrect. This is called because we caught it. So exception interrupts do stuff, gets handled here, and then this is called. This is incorrect. Called. Okay, so we know how to throw exceptions, how to handle. You can catch, and inside the catch block you can run basically arbitrary code. You can catch exceptions by reference, that's the normal way of doing it. You can catch by value as a normal value, pass by value semantics, a copy is made. You can catch by pointer. Pointer is just a built-in type, which means you can catch pointers by value. There is a tricky question as who is going to delete whatever the pointer points to. Difficult to arrange in a large system that deletion happens and happens only once, so usually not recommended. Now, here I said catch int by reference. What if it's a double or if it's exception? You don't catch it. This catch block does not catch it. Well, if you want to catch anything, you can use catch ... and it catches any type. Of course, you don't know what type you caught. You can catch multiple types. So we're going to catch an int. This is catching std exception by reference. Now, you don't normally throw std exception. You throw anything derived from std exception. Your normal polymorphism rules work. If you catch by reference to a base class, you get all derived classes. And if it wasn't any one of these, here is catch ... Okay. So since we spoke about derived classes, can you throw a derived class? Sure. Why not? So let's look at this. This is, I specifically focus on this because this gets you sometimes. Here is a derived class, base class, throw reference to a base class. Here we have derived class, and we're trying to catch derived class because that's what we actually passed in. This is a base reference, but it points to a derived class. Surprisingly enough, this one fires. Not this one. And that's because exception throwing is static. It's the type of exception you're throwing determines at compile time, not at runtime. Throw is not a virtual function. So whatever the type of, whatever this type is, that's what is thrown. You can think of it as a copy being made, which it actually can be, but doesn't have to. There are no virtual copy constructors. If you're copying a type, a base type out of the derived type, you get a slice. You ripped out the base type out of the derived. Can you throw polymorphically if you want to? Yes, using virtual functions. You basically make the throw itself into a virtual function. Like here is a function raise. In the base class, it throws the base class exception. In the derived class, it throws derived exception. And now, if this is really a reference to D will actually be thrown. Because the polymorphism occurs not at the point of throw, but at the point where we decide which of these functions to call. Here, it'll call derived. Okay, can you throw inside the exception handler, inside the catch? Yes. You can throw anything you want, but there is one extra option open to you. You can this one, throw with no type, throw nothing. This throws the current exception. Whatever you were handling gets rethrown and continues to propagate. This is actually sometimes useful. Sometimes people modify exceptions. If you catch by reference, you can do something to that exception and rethrow it. And here is an interesting idiom that allows you to have some code reuse in your exception handling. So let's say you have many places which can throw, but you have some unified code that you don't want to copy that you want to use for handling those exceptions. This is called exception dispatcher. So here is your place that can throw and catch. You call the dispatcher gets called inside the catch block. The only thing it actually does is it rethrows. It rethrows the current exception and it handles it here. Okay, so this is just so when we see exception syntax in the slides, we know what we're talking about. Since the main goal is to convince you to not be afraid to use exceptions, well, why would you be afraid to use exceptions? What's wrong with exceptions? The main problem that people bring up is exceptions run in a separate control flow. Now, exception handling code is what you have inside the catch blocks. So the normal execution is suspended, and you have the control jumps out of the middle of your normal code into the catch blocks. The catch blocks are difficult to write because why did you jump out of your normal control flow? The normal state of the program has been disrupted. The current state is, well, nobody knows what exactly it is. Something went wrong. So the program is probably already in a bad state. Now, the goal of exception handling is to actually undo this situation and restore the well-defined state. In order for us to do that, we have to have some level of guarantees about what can we do safely. If once the program is in a bad state, you cannot do anything for sure, there is no guaranteed way to recover. So you have to have some guarantees. Okay, so going back to our alternatives, exception-safe code is hard to write. That is actually correct. It's not, however, a good reason to avoid exceptions, because Any code that maintains a well-defined state is hard to write and about equally hard to write. Well, let's look at this. Okay, if you don't use exceptions, what do you use? You use return codes. Well, here is your error codes. So we create widget. If something failed during creation and we got null, you return an error code. The main difference is error codes use the same control flow. So you would have returned the value anyway, even if it succeeded. So you use the same control flow. The second main difference is return codes can be ignored. Everybody knows that printf actually returns something. Who always checks with the return value of printf? Okay. Exceptions cannot be ignored. They will terminate if you try to ignore them all the way up. Return codes are constrained by the return value, which means you have to have a return value that is otherwise impossible. Of course, the other option is you add an extra parameter for your return code. Exceptions can be of any type or of multiple types. There is a price for that. And the price is exceptions are not easily visible in an interface, whereas return codes are. So this is the declaration of a function. Well, what does it return? A pointer. What can it throw? Anything it wants. That's the manifestation of the separate execution channel. Okay, C++ 98 had throw declarations. C++ 11 added no except. Yeah, they don't quite help all the way. First of all, it's not a compile time check. Even no except, which can be evaluated at compile time to check whether you have a guarantee for no except, doesn't actually guarantee that it won't throw. The only thing it guarantees that the program will die if it tries to throw. Furthermore, the functions that are no except or no throw can throw inside, they just have to catch it. This actually guarantees that the exceptions don't escape. Well, it guarantees that exceptions don't escape at the cost that you may terminate. Okay, there is one place where you cannot use return codes. Constructors have no return values. Constructors can fail, just like any other functions. Oh, there is another place. Destructors have no return values. Well, it would be kind of hard to deal with destructor failing because the object is going away one way or the other. Destructors also should not throw. The reason for that is in C++, you can have one exception propagating at any given time. Destructor can be fired as a part of stack unwinding when an exception is propagating. If destructor itself throws, you now have two exceptions in flight, the runtime system calls terminate immediately. So technically you can throw, it will compile, and if it actually throws during stack unwinding, the program terminates. So summary of the differences. Exceptions cannot be ignored, return codes can. Exceptions have their own execution flow that never gets exercised unless you throw. Return codes have the same execution flow. Return codes you have to propagate on every stage. If you're not ready to handle it, you have to return again. Exceptions will do it by themselves. Implicit interface versus explicit interface, more constraint on the types, and the exceptions can be used in constructors. Okay, exception safety is really hard. That's why some people avoid it. Here is a very simple function. Open the log, create a widget, log the creation of the widget, close the log, return the new widget. What could possibly go wrong here? Everything, yes. Okay. Open can throw. What happens if open throws? Nothing really. The new expression, including the constructor, can throw. What happens if new expression throws? Log file remains open. Presumably, the recording can throw. What happens if that throws? Well, we throw, we don't return the pointer, but we did allocate it. So now there is no way to get to that widget anymore. So the widget is leaked. that wouldn't be half as bad if it was just the memory. What if a construction of the widget takes a lock that you must unlock later? Wouldn't be a very good design, but what if it happened? Now you leaked an open lock. Well, okay, that's why you shouldn't be using exceptions. See how many problems on one slide. Return codes are much better. Let's say that everything here uses return codes. L returns a return code, just like a printf. Never happens, ignore it. A new expression can return null. Nah, probably wouldn't happen, never mind. A record can fail, return an error code. Probably won't. Okay, now let's actually use error codes. I said use error codes. Let me highlight use error codes. If it opens, if open failed, return null. If widget creation failed, return null. If record fails, return null. Well, all of the same problems that we had with exceptions actually can happen here, only the code looks uglier. The fundamental problem that we're facing is not handling exceptions or writing exception-safe code. The problem is handling errors and writing error-safe code. The fundamental requirement is, after an error happens, the program somehow must remain in a well-defined state. And what's a well-defined state? Well, there are several levels of well-defined state. At the bare minimum, no resources must be leaked. That's called basic error safety guarantee. If you're using exception, it's called basic exception safety guarantee, but in a more general situation, we can call error safety guarantee. Ideally, whatever operation failed is cleanly undone as if it was never attempted. That is called strong guarantee. It's hard to do because the only reason you're even there is because something is already wrong. Okay, in practice, people who write exceptions, that's kind of your first line of defense. People who usually don't think about these guarantees. The most common guarantee you have is, we don't use exceptions here. That's a kind of no-throw guarantee. Assuming your libraries don't throw, assuming your runtime system doesn't throw, anybody uses operator new, well, that can throw. Dynamic cast can throw. Okay, you still need to handle errors somehow, so there are alternatives. The probably most common alternative is this one. No guarantees at all. So if exception is thrown or if error happens, the state of the program is undefined and continues to be that way. Now, if you actually try to do it right, then you have to consider these, at least these two fundamental guarantees. The basic guarantee, and here I talk about exception safety, but if you use something else for handling errors, it'll be your basic error safety guarantee. The program must always remain in a well-defined state. In a well-defined state, some actions are possible with well-known results. Some other actions may be impossible or lead to undefined results, but at least some set of actions that is known is still possible and is well-defined. So, for example, if an object throws, you can still call some member functions. Maybe only destructor, but at least you can destroy the object. Now, well-defined state is not necessarily a very useful state. Calling terminate or abort is a well-defined state. Remember, I mentioned not very useful. The opposite extreme is a strong guarantee, and the strong guarantee is what's sometimes called commit or rollback semantics. Any action that you take will either succeed or be undone as if it never happened. This is very hard to do. It may be very expensive. It may be impossible. Now, it's sometimes used in a more narrow context. For example, on some library, but even on libraries it's very expensive. STL, which could never be accused of avoiding writing complex code, does not provide such a guarantee across the board. So in practice, you have some kind of medium. For example, STL provides strong guarantee on certain functions. And it's documented which ones. For example, STL pushback either succeeds or throws and makes no changes to the container. Now, it doesn't actually make no changes. It makes changes. It just throws them back. Or at least it may make changes, because you may throw sometime halfway through pushback, in which case some of the changes were already made. It just guarantees to undo them. Other operations provide basic guarantee, which means that certain invariants are maintained, at least destructors. At the very minimum, STL gives you the guarantee that if it throws, destructors may be called. No resources such as memory, logs, threads, and so on are permanently leaked. What do I mean by permanently? At the point of throw, not all resources may be cleaned up, but you do have objects that own them. So if you start destroying stuff, eventually you will release those resources. So, and in addition, STL gives you additional guarantee that is very important. Certain operations such as swap and all destructors provide the no throw or no accept guarantee. It's actually very important that swap provides a no throw guarantee. Okay, exception safety is just a particular case of error safety. If you happen to convert if you have an exception program and you convert it all to error codes, well, I don't know why you would do that, but if you imagine an exception safe program and then write it in terms of error codes, it's actually just, if you do it correctly, it's just a different syntax. Your error handling will be basically the same. So let's think in general, ignoring exceptions versus error codes. What do you do if your program encounters an error? The first option is you ignore it and hope it doesn't happen. The second option, you ignore it and you don't have any hopes. Then the more practical one is you maintain certain level of invariance. That's a basic guarantee. Or every operation follows commit or rollback. That's a strong guarantee. In a program that remains in a well-defined state in the face of error, some level of guarantee must be given, whether you use exceptions or not. So throughout this lecture, we'll have several kind of take-home points accumulated, and the first one is know your error handling guarantee, not exception handling, error handling guarantees. What do you do and what do you promise when the program enters an undefined state and something abnormal happens? Okay, exceptions are just a syntactic tool. Here is a program that uses exceptions. Try creating widget, catch it, close the log and rethrow. Try recording it, catch if something fails, delete a widget that we created, close the log and rethrow. This looks very much like error codes. I can rewrite it with error codes and it'll look almost the same. Well, let me do that just to prove. Here it is. These things look very much like catch blocks. There is very little difference if you actually bother to handle errors either way. So it's useful to think in terms of handling errors, not the details of whether they're expressed by exceptions or not. So let's look at this kind of pseudocode. From this point forward, so here if an error happens here, we just return. And we may return through the normal channel or through exception channel, but we basically just, we don't do any of this. If an error happened on this line, we must close the log and then return. If an error happens on this line, we must delete the widget, close, and then return, and so on. Another way of thinking about it is, from this point forward, if anything happens, we have to close the log. From this point forward, if anything bad happened, we also have to delete the widget. We still have to close the log, but we also have to delete the widget. Again, this is not C++. This is annotations for us to pay attention to. So we need some kind of action that will happen automatically from certain point on until the end of the scope. And then from this point on, and another action will happen, like delete W, and the first action will still happen. You know any feature in C++ that automatically runs code at the end of the scope? Destructors on local objects. There is a wrinkle, however. There is slight subtle difference between closing the log and deleting the widget. Closing the log must always happen, even in the normal flow. Even if there is no error, at the end of the scope you need to close the log. You better not delete the widget if you're going to return the pointer. So there is a subtle difference between these two actions. One happens in normal and error handling channels, and one only happens in an error handling channel. The guideline here is the normal cleanup should be done in the normal channel. Well, let's look at some code that would do this. Now, this is basically a unique putter of C++11. The only reason I wrote my own is I want to show you exactly what's going on the inside. I didn't want to lie to you about implementation of unique putter. It has a little more code than I'm going to show, so I created a kind of simplified unique putter. And you would use unique putter in reality. So first of all, we have this log guard that in the constructor it opens the log, in the destructor it closes the log. And then we have basically a unique putter, which I call scoped putter here. Constructor just grabs the value of the pointer and the destructor deletes it. Okay, now here is our log guard of log. The constructor opens the log. The destructor will close it. The destructor will close it no matter how we exit this scope. If we return right here, log gets closed. If we return all the way on the bottom, log gets closed. If something throws in the middle here, log gets closed. Thank you. Okay, this is great. Here is our scoped pointer, which, as I said, is just a unique putter. Captures the widget. If anything throws in here, let's say this record throws, then the destructor of the unique putter will fire and delete the widget. This is great. If but at the end of the scope, the destructor of the unique putter will fire and delete the widget that we just returned. That's not so great. Okay, so we have converted an error handling problem to a resource management problem. We just haven't managed the resources quite right. So resources that are acquired within the scope must be released within that scope. That's your normal local classes, unless you want to hand off the ownership, and that's the classic resource management problem. So for log, we're good. We don't hand ownership anywhere. For the widget, we need to hand off the ownership to the caller. Okay, let's add some more stuff to our scoped putter. Again, this is verbatim how it is in unique putter, only there is more stuff to it. But it behaves basically as if it had this. And that's why I didn't call it unique putter, because I don't want to write more stuff and I don't want to pretend that it's as simple as this. There is a release function. What the release function does is it returns the pointer that was captured inside the unique putter, and it resets the pointer to null without calling the destructor. That's important. You can always reset unique pointer to null by just assigning null to it, but it'll call the destructor. Well, this one you can't reset to null because it doesn't have assignment operator. Okay, so at the point where we have to release ownership, where we survived up to here, errors did not happen. If we didn't survive, the destructors of both of these would do the cleanup. We survived up to here. Now it's time to relinquish our ownership on the widget. So we can return the release. The important part is basically there shouldn't be any errors after this, at least not the ones that would force you to delete the widget, because at this point we gave up the ownership. Well, the guideline. Use resource acquisition as an initialization paradigm to automate resource cleanup in both normal and exceptional channels. And actually, this is a standard factory function, so this is actually a simpler way to write it with a unique putter, because unique putter will move the object from, in C++11, it will move the pointer from here, from this one, to the return value. And when you move, the destructor on the temporary will not, well, the destructor on the unique pointer will fire, but it will not destroy the widget because you moved it out. It will be null inside. Before C++11, you could replace unique pointer without a putter. And this is actually one of the few places where it actually worked and did exactly what you wanted. Now, this is all about exception handling. So where are my try-catch blocks? How do you handle exceptions without try-catch blocks? There aren't any. And this is a very important point. This program handles errors correctly. It handles errors regardless of what mechanism you actually use for handling it. If you put returns here, it will still handle the cleanup correctly. If you throw, so if any of these can throw, errors are handled by the destructors. If, let's say instead of throwing, you check a return code of record and return null. Because you return null from here, you did not move the widget from the unique pointer, so the destructor will fire. So this is essentially mechanism agnostic. And that's the whole point. Correct error handling knows very little about the syntactic tools you use to handle errors. So always think about handling errors. Don't think what happens if this throws. Think what happens if this function encounters an error and has whatever abnormal return it can have according to its syntax. How are you going to recover? Mostly error handling is about not leaking resources and maintaining invariants. Now, your normal programming is also to a large degree about not leaking resources and maintaining invariants. While we're focused on not leaking anything if error happens, we also don't want to leak anything if errors do not happen. That would be bad. So most of the cleanup actions actually have to be done in both normal and error control flows. So do them and do them without copying the handling code. Do them in a way that works for both normal flow and the error flow. At some point, you have to actually handle errors explicitly. So if you're using exceptions, you have to catch them. If you're using return codes, well, first of all, you always have to check and return. So you have to handle them explicitly for that. That's why a well-written exception code has very little exception syntax, because you only catch stuff when you need it. For the most part, the automatic return happens invisibly to you. A well-written error-safe code based on return codes has explicit code to check return codes every time. Other than that, it still doesn't have any other special handling code. It just check, return, check, return. The cleanup happens automatically. So why would you catch? Well, you have to stop exceptions at some point from propagating. If nowhere else, you have to do it in main, otherwise it's a terminate. Now, another reason is if you want to change how you report errors. You can catch exceptions and then propagate the error in some other form. You can use return codes, you can throw a different exception. Rarely used, you can modify the exception and rethrow it, which is just a particular case of the previous case. So these were all reasons to catch. This one is not a reason to catch. do the cleanup after the error. Don't do it. Don't cache to do the cleanup. Well, let me show you a more more complete example. So the guideline is only use cache blocks when you actually have to catch exceptions, not when you have to do the cleanup. Okay, let's talk about what not to do. Let's talk about unnecessary error handling. Manual error handling, deleting raw pointers, closing files, reclaiming resources. This is what not to do. So don't be confused. There are things to do and there are things to not do. Don't mix the two. This is not exactly std vector resized, which is why I put a capital V here, but it's close enough. So what does the resize do? Well, it allocates new memory. So vector is basically a wrapper around a big array. It has a contiguous buffer, so if we want to resize, let's say this resize, it always doubles doubles the memory. The real resize takes a parameter, but that's unimportant here. Now allocate. Okay, if that fails, you just throw. Nothing changed. All right. Then, because we just allocated new memory, we have to copy the existing data from our current buffer. We have, this is a new buffer, so we have a current buffer. We have to copy the existing data from the current buffer into the new buffer. And that can throw, because it's a copy constructor, it can throw. So if it throws, we have to clean up the memory. We have to deallocate the new buffer and rethrow the exception. Okay. This actually has a, oh, and we also have to destroy whatever we already copied. So this would follow commit or rollback semantics if an initialized array copy was done right. So let's look at an initialized array copy. Here is an initialized array copy. This is actually an STD algorithm. It's slightly more complex than that, but that's the basic idea. Again, we're going to try to copy from begin to end. Just increment the from. This is the from pointer. This is the source. This is the destination, and we're just going to placement new. This calls the copy constructor. This constructs a new element in this location. That's a placement new. If something goes wrong, we have to call destructors, because this is a placement new. We didn't allocate any memory, so we can't call delete, but we still have to call destructors. Yeah, you can call destructors explicitly. So if something went wrong, we have to call the destructors on anything that succeeded. So maybe 10 objects got copied, 11th thrown. Well, you have to delete the 10. Okay, so if copying fails, all the copies that you already made are destroyed. Was there a question? No? Okay. Well, this is correct, but badly written. The previous example was correct, but badly written. Here is how you do it without an explicit catch. Here is our buffer. It has constructor, and it has destructor, and it has a no-throw swap, or in C++11 it would be a no-except swap. Very important that this does not throw. You'll see why. Okay. We create a buffer. We do an initialized array copy. We copy the elements, and we swap the buffer. This is why it's important that this doesn't throw, because at this point you would not be able to recover from the error anymore. Oh, you destroy, yeah, you destroy the old, you call destructors on the old stuff. Destructors don't throw, because again, at this point, you would not be able to recover from the errors. Very important that destructors do not throw, very important that swap doesn't throw. If, however, an initialized array copy throws, it does whatever it wants inside, it then rethrows, and the destructor of the buffer cleans up the memory without the explicit catch block. Okay, what about uninitialized array copy? Well, here is our little handy copy guard, and very strange calling signature, destination, destination. There is a subtle difference. One captures the pointer by value, and one captures the pointer by reference, which means one of them tracks, this is the begin, it tracks what the destination was when you called it. This is the end, it tracks what the destination is currently. And we're advancing destination as we copying values from begin. So this destructor will destroy from the old original value of destination to the current one without any catch blocks. Compare with this catch block. This is basically the same code, only now there is no catch blocks. Now there is one trick, of course. We don't want that destructor to destroy everything if this copy succeeded. So we have to do the equivalent of the release. On success, we have to release. Thank you. Okay, so don't do manual error cleanup. Do automatic error cleanup. If you already got so far, you have very little try-catch in your program. So now do take advantage of the language features of basically at this point, exceptions is just a return code that you don't have to explicitly check, and you don't have to say if error return. That's basically what exception does for you. Everything else is exactly the same. Here is your error safe code using return codes. Here is your error safe code using exceptions badly. Don't do this. Here is your error safe code using exceptions correctly. The scope guard will do whatever actions you need to do on exit, assuming you have some cleanup on exit. So this is just a placeholder for resource acquisition as an initialization object. So do prefer exceptions to error codes for the simple reason that they actually remove few lines of code if error return. Okay, we're now going into kind of a system design area. So, okay, now we have we know how to write our error safe code. We know how to use exceptions. So at the kind of microscopic level, at the level of one function, we're good. What about the entire system? Well, that's where you have to think. Usually happens when two different groups write two different subsystems. One of them has their own exceptions list, and the other one has its exception list. Now, that's why exceptions are bad. That's why you use error codes. No, same. One of them has its own enum for error codes. The other one has its enum for error codes. Exact same problem. This could actually be a good thing if you need to cross a system boundary and change how you handle errors. If this wasn't by accident, if you actually have different subsystems with different error conventions, not just different kinds of exceptions. You could be changing from exceptions to return codes or back. So in general, consider your error handling, which could be exception handling or not, as a part of your overall system design, even though it doesn't show in the function declarations. When you design system, think of it as a part of your design. How are you going to capture and express errors? Well, this is an example of converting. So this is an old legacy system. Well, who uses jukeboxes now? This is a brand new shining database that uses exceptions. Of course, it's C++11. So this is the conversion from one to another. Fine, if you have to bring those two systems together and change the way you handle errors, that's what you do. You can repackage errors at system boundaries, no problem. So, in fact, system boundaries are a good place to handle errors in general. Within one system, you have your automatic cleanup going. When you leave that system, you have the kind of broader concept of a well-defined state. Nothing really, don't abandon your system in a poorly defined state. That's where you should do the error cleanup. So exceptions do make it easier. But most of the time we work on legacy code, and a lot of legacy code doesn't use exceptions. It's difficult to rewrite your entire code base to use exceptions. So how to start using exceptions in small doses? The answer is, don't worry so much about it. The goal is how to start handling errors correctly if you don't. Well, here is a little program which doesn't handle errors. Close has an error code, by the way, can fail. Who checks error codes on file close? Okay. Don't neglect the advantages of exceptions, but think first of making your program error handling correct. If you do, then you will discover that actually to switch to exceptions is a very little burden for the most part. And if you have to explicitly handle errors, including converting the different types of error handling, do it at the system boundaries. Okay, legacy code and third-party code. So as I said, convert error codes at system boundaries. The hardest part is this last one. You have to know what a well-defined state is, whether you use exceptions or not, and there is no shortcut for that. You have to know your system. You have to know what resources could be in use and what resources could be leaked. That's actually the hard part of being exception safe, but it has nothing to do with exception safety. It has to do with error safety. And yeah, error handling is usually not visible in the interface, which means you rely only on the documentation. Unfortunately, error handling is usually the worst documented part of your interface. Here is a kind of a flip side, just to show you. If you're integrating third-party code, but kind of backward, if you're writing a library, not you're using a third-party library, but you're writing a third-party library, well, there is this trick where so the file system, the file system proposal now uses, before the standard uses this trick, so it's not all bad. Basically, provide function overloads for all your functions. One option is with exception handling, and the other is a no except with error codes. This is the syntax that the file system TS uses. You can also do it like this. Here are the choices at compile time, here are the choices at runtime. The advantage of this is that they can actually put no except on the overload that has error codes. So convert it gradually, focus on error handling first. Okay, and we have some time for questions, right? Okay, I have some additional reading in the slides, and I believe CppCon will publish the slides at their GitHub. Okay, I do have a bonus guideline. Who wants to see bonus guideline? Now, warning. If you were asleep during this talk, now is the time to wake up, or your dreams will turn to nightmares. Because this is a bonus nightmare material. C++ now supports threads. Well, big deal. In practice, C++ supported threads for a very long time. Supported POSIX threads on Unix systems. What's POSIX threads? Oh, we all know what that is. pthread create, pthread join, and all pthread lock, unlock. Who here have seen this one? pthread cancel in the POSIX standard. If you cancel a thread by pthread cancel, do the destructors fire? Who thinks they do? Who thinks they don't? glibc implements p3 cancel as an exception. Destructors do fire. Stack is unwound. Yay, that's great. Is it? You just caught pthread cancel and didn't rethrow. Well, in practice, it doesn't quite do what you think it will do. It doesn't completely silence pthread cancel. Pthread cancel is a special exception. You get abort instead of pthread cancel. Well, it gets actually worse. You can solve this problem. You can solve this problem when you're dealing with glibc, because glibc specifically implements pthread cancel as an exception. So any catch ... can trap pthread cancel. Well, you can specifically catch for this is what you should be catching if you want to specifically grab the pthread cancel, and you probably should reserve it. You'll probably want to if-def it in your compilation, because this is a type that is only present on glibc-based Linux systems, well, any glibc-based systems. It's not the worst part. This was just, disturbing dreams. The nightmares part come right now. Pthread cancel can interrupt your thread in any cancellation point, which means any cancellation point can now throw, including those inside your noExcept functions, including those inside your destructors. How often do you have destructors that close files? Who has destructors that close files? Close is a cancellation point, which means close can throw if a cancel is pending. Avoid pthread cancel. Okay, question?
You said it unwinds the stack pthread cancel because it's an exception. Would the exception then call this action not unwound?
As I said, it's a special exception. It's effectively caught at the outer level of the thread where pthread exit would be called. So the compiler knows that this is just like it knows to abort if you decide to ignore it, it also knows that this exception is always caught and the implied handler is pthread exit. Any more questions? Well, go and use exceptions then.